All right, in this video, we are going to be talking about scientific notation. Specifically, we're going to be talking about making sure that we know how to convert numbers into proper scientific notation. And we'll talk more about what that means in a second. And we're also going to make sure that we understand how to convert small numbers into scientific notation. To begin with, we have to understand that the relationship between the coefficient and the term is really important. If we take a look here, we can represent the same value in a lot of different ways. 400, which is really 400 times 1, right, is the same thing as 400. However, if we take the coefficient and we divide it by 10, 400 divided by 10 is 40. We just move the 4 over one place value to get to 40. Then, as long as we increase the term by a power of 10, we still get 400. And same thing again, if we take 400 and divide it by 10 twice, or decrease it by 2 powers of 10, then as long as we increase the term, which was 1, now by 2 powers of 10, that's where 10 squared comes from, we're still going to get 400. And if we decrease it by another power of 10, and increase this by another power of 10, we still get 400. As a matter of fact, as long as between the coefficient and the term there is a 4 and 2 powers of 10, it's going to be 400. Here, the 4 and the 2 powers of 10 are all in the coefficient, right? That's 400. Here we have a 4 and 1 power of 10, 4 times 10 or 40, and then another power of 10. So we still have a 4 and 2 powers of 10. Here, the 4 is the coefficient, and the powers of 10 are represented all here, which is what we want. This is called proper scientific notation, where the coefficient is just the place value, and then the term is the power of 10 that represents that number. Here we've actually gone 1 to the other side, right? This is 1 less power of 10, 1/10, and then 3 powers of 10. So we still get 400. And the way I like to think of it is, it doesn't really matter. If let's say that this was a big scale, right? And we were weighing this. A big scale here, and we're weighing how much this is. Right now, we have a pile of 5 and a pile of 3. If we take 1 away from here, as long as we add 1 over here, it doesn't make any difference to the overall weight. In this situation, we've removed the power of 10 from here, but added it over here. So we've just shifted that power of 10 from here to here. So it made no difference on the answer. This is going to be an important thing to realize as we're converting numbers into proper scientific notation. Oops. So let's take a look at a couple of examples. Here we have 400. What we want it to equal is 4,000, which is 4 and 3 powers of 10, right? 1,000 is 10 times 10 times 10. Well, this is only 2 powers of 10. We need to move this to the left one, or add an extra power of 10. So to do that, we just multiply it by 10, and we get 4,000. Here we have a 4 and 1 power of 10, and we need a 4 and 3 powers of 10, so we need to multiply it by 2 powers of 10. And now we have a 4, 1 power of 10, 2 powers of 10, for a total of a 4 and 3 powers of 10. Here, this is going to be the proper scientific notation. The coefficient is just 4. It's the place value. And now how many powers of 10 are there? Well, there's 3. And you can see if I decrease by another power of 10, I increase this. If I decrease by another power of 10, I increase this again. In general, in scientific notation, the purpose is for the coefficient to be a single digit in the ones place. Now there can be decimals behind it, but it has to have a single digit in the ones place. And then the term tells us the place value. In order for that to work, the coefficient must always be a number between 1 and 9.99999. Basically, the coefficient always has to have some number in the ones place and not go past 9.99999. 0.35, that's less than 1. There is no digit in the ones place. So we need to add a power of 10 here. And if we add a power of 10, it's going to become 3.5. Now we have a single digit in the ones place. But since we added a power of 10 here, we need to take a power of 10 away from here. Picture those rocks, right? We added 1 extra power of 10 here, so we need to take it from here. So instead of 10 to the 4th, to keep this equal, it's now going to become 10 to the 3rd. So here's a good little practice exercise. I'm asking you to write the following numbers in scientific notation. Well, this has a digit in the ones place, but it's also got a digit in the tens place. We can't have that. It can't be bigger than 9.99999. So I need to remove a power of 10. And when I do that, it becomes 4.63, which is great. There's a number in the ones place. It's not bigger than 9.99999, but it's also not less than 1. But since I took a power of 10 away from here, I need to add it over here. So this becomes 10 to the 5th. Same thing here, and I apologize, my font did not work out very well. This is 10 to the 8th, not 108. So I have, hey, this is not a number between 1 and 9.99999. This number is too small. If I add 1 power of 10, everything goes to the left one. Well, that's still not big enough. I need to add 2 powers of 10, and this becomes 1.2. But if I added 2 powers of 10 here, what do I have to do here to keep it equal? Well, I've got to remove 2 powers of 10. So that becomes 10 to the 6th. Once again here, this is 10 to the negative 5th. I've got 53.1. That's too big, right? That's bigger than 9.9 repeating. So I need to remove a power of 10. And everything, when I remove a power of 10, I'm dividing by 10, right? So everything moves to the right one. So I wind up with 5.31. But since I removed a power of 10 here, I need to add a power of 10 here. Well, now you got to go back to thinking about integers. What is negative 5 plus 1? Well, that's negative 4, right? It's gone up 1. Negative 4 is 1 bigger than negative 5. If you need to, draw that number line out, right? This is this is further to the right than negative 5, so it's bigger. We just did that. Oh, look, my font's good there. All right, so moving on. We must also understand what it means when we have a negative number as an exponent. And we've already talked about that some in class, in the sense that a negative number exponent is just further down the place value, right? So 10 to the negative 2, well, the ones place is 10 to the 0. So the tens place is 10 to the negative 1. And the hundredths place is 10 to the negative 2. So this is the same thing as 1 over 100, or 1 over 10 squared. So let's take a look here. We're going to try and express this number 4 thousandths in scientific notation. Well, we know that's the tenths, that's the hundredths, that's the thousandths. So this is 4 over 1,000. Now we also know that 10 to the negative 3 equals 1 over 1,000. So if I multiply 1 over 1,000 times 4, that's going to equal 4 over 1,000, right? Because this is really 4 over 1. We multiply across. 1 times 4 is 4. 1,000 times 1 is 1,000. So 4 times 1 over 1,000, which is also 4 times 10 to the negative 3, equals 0.004. And this is all converting small numbers into scientific notation means. It's really no different than large numbers. So let's take a look at some problems. I've given you the problem 2 times 10 to the negative 5th, and I've asked you to write the fractional equivalent and the decimal equivalent. So let's take a look at what that looks like. We need to realize which place value 10 to the negative 5th is. Well, there's my ones place, my 10 to the zeros place, right? So my tenths place is 10 to the negative 1. And then my hundredths place is 10 to the negative 2, negative 3, negative 4, negative 5. 10 to the negative 5, and that's 100, 1,000, 10,000. This is 1 over 100,000. It's a pretty small number. That means the distance from 0 to 1 on the number line is subdivided into 100,000 little segments, right? So now our place value is 1 over 100,000. What's my coefficient? It's 2. So if we multiply this by 2, we wind up with 2 over 100,000. Oops, sorry. And in decimal notation, let's see, this is the 1, 2, 3, 4, 5. This is the 5th place value to the right of the decimal. So 1, 2, 3, 4, 5. There's a 2 there, right? That's the digit in that place value. So this is the fraction equivalent of this. And this is the decimal equivalent of this. I'm going to jump over and do one of the hard ones, and then we'll move on. I ask you to convert this into decimal and fractional equivalent. All right, so 10 to the negative 4. Let's take a look at what that looks like. Here's our decimal, right? This is 10 to the negative 1, negative 2, negative 3, negative 4. That's 1 over 10, 1 over 100, 1 over 1,000, 1 over 10,000. And what number is in 1 over 10,000? Well, it's a 4. And then you can see to the right of that is a 3, and to the right of that is a 2. Fabulous. So we've got 0, 0, 0. So this is the decimal equivalent. And now we need to take a look at what the fractional equivalent is, right? So the fractional equivalent of this is going to be 4 over 10,000 and 3 over 100,000, right? And 2 over 1 million. That's each one of those place values. So there's our fractional equivalent, and there is our decimal equivalent. All right, so moving along, let's take a look at what comes up next. A couple contextual problems. The distance from the sun to Mars is 1.416 times 10 to the 9th miles. And the distance from the sun to Earth is this number here. And I ask you to write both of these numbers out in decimal notation. So let's do that real quickly. I'm going to move all of this kind of over so I have a little extra room. So that 1, what's the 10s to the 9th place? That's to the 0, to the 1, to the 2, to the 3, to the 4, to the 5, to the 6, to the 7, to the 8, to the 9th. So there's a 1 there, and then to the right of that's 4, 1, 6, and the rest of these are zeros. So that's my decimal equivalent. That's how many miles the sun is to Mars. That's an accurate number. What is that? That's 1,416,000,000 miles. And the distance from the sun to the Earth, let's take a look. That's 10 to the 8th. 0, 1, 2, 3, 4, 5, 6, 7, 8. It's a 9 with a 3 to the right of it, and then the rest are zeros. So what is that? Let's take a look. That's 930 million miles. And now I say determine how much further Mars is from the sun than Earth. Well, we can just subtract, right? These gonna line up. Here, I'm gonna use my line so it's a little bit clearer. That lines up. That lines up. That lines up. 10,000s, 100,000s, millions, 10 millions, 100 millions, and then billions. So let's do that math real quickly. So we know all of these are zeros, right? Now, what's 6 minus 0? Well, that's 6. 11 minus 3 is going to be 8. And then 13 minus 9 is 4. So the distance from Mars is 486 million miles further from the sun than Earth is. And we could also determine that's the distance from Earth to Mars. And now I want you to put that back in scientific notation. What place values the 4 in? 0, 1, 2, 3, 4, 5, 6, 7, 8. 4.86 times 10 to the 8th. All right, so I give you one other problem with small numbers, which I'll let you kind of pause the screen and work out. And I give you a few other problems to convert in scientific notation, but that's pretty much the bulk of what this lesson's about. I hope this helps, and thank you so much.